All right, so welcome to our webinar series. This session is why are new indoor air quality metrics needed. This course is approved for 1 hour in continuing ed, GVCI, AIA HSW, NARI Green, Certified Green Professional, AIBD. And something new we're going to be doing is Certified Passive House Consultant for this course as well. I am your moderator. My name is Brett Little. I'm the executive director here at the Green Home Institute. The Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation of the construction of the places we live. If you're looking to do a green building certification project as well, we can help you out with that. And then also a huge thanks to everyone who supports us and allows us to do what we do, our members, our Green Raiders, our volunteers, our presenters, our board of directors, and our major sponsor, Andersen Windows. Check them out for all your fenestration needs, along with Panasonic ventilation. All right, so very excited here to have Ty Newell. Ty is the co-owner and co-founder of Build Equinox, a company devoted to inventing technologies for healthy, comfortable, and sustainable living. He retired from the University of Illinois in 2007 as an assistant dean in the College of Engineering, has advised 70 master's and doctoral graduate students, and is an emeritus professor of mechanical engineering. His degree is mechanical engineering of 74 from University of Michigan, all right, like that. And then also his PhD in the 80s from the University of Utah. He has lectured around the world on indoor air quality, comfort, solar energy, building energy efficiency, and resource conservation. He was the keynote to address the Solar Energy Society of India's 25th Silver Jubilee in, I'm not going to mess that word up there, but, and then also involved in a conference, Turkish ASHRAE at Istanbul, Turkey. He's been a Fulbright scholar at the a university in Argentina. I'm not going to mess that one up either. And I've been involved with the European Union, Switzerland, United Nations Workshop, and a leader in Beijing, China, and academic leader down in Mexico as well. Ty lives in a 100% solar-powered home in Urbana, Illinois. So hopefully, Ty, if you're broadcasting from your home today and a cloud goes over, we probably won't hear you, so we'll know why. And as the first home with an Illinois municipality be permitted for rainwater harvesting use, Build Equinox is located in a 4,000 square foot Morton building in Urbana, Illinois, and also is 100% solar powered. So again, if you're broadcasting from there, Ty, we know, of course, a cloud goes over, we know what happened. So take it away.
Well, thank you very much, Brett. I hope the connection works well, and I appreciate Brett and the Green Home Institute coordinating this and giving us the opportunity to present this topic. It is a sunny day here, so there shouldn't be any blips as far as the energy supply, and it's an exciting time in seeing all the topics that the Green Home Institute has coming up on how to live on our daily allowance of solar energy. I was just working with a friend this week who's a local installer, and just seeing that now the price of solar panels and the price of inverters are well below $1 a watt for inverter and panel, and that the installation cost is dropping below $2.50 a watt. I mean, this is 8 cents a kilowatt and less electric without any tax credit. So it's an excellent time. So this talk is about air quality and some metrics that we've developed here at Build Equinox. And the goal of this is to talk about these metrics and how we feel these will help us to better understand the value of air quality around us, and metrics that help us understand when we're doing okay and when we're not, and the adjustments we may need to make. I'm sitting in the middle of nowhere, Urbana, Illinois, and it's a great place here. things love to grow here. We have just the right amount of water and sunshine to be able to live comfortably. And our mission here at Build Equinox, our company, we do a lot of research, a lot of education, and our overall goal is to use our backgrounds as engineers. Ben Newell, who's our president, Alex Long, and myself, all three of us are mechanical engineers, but working on technologies that we feel are important for us to live on our daily allowance of solar energy, to live healthy, to live comfortable and sustainable lifestyles. That is, how do we keep improving the quality of life and doing that with less of an impact on resources? And I think Aldo Leopold said it best. Aldo Leopold, the founder of the modern era of natural resource studies. How do we live on a piece of land without spoiling it? And that's what we'd like to do. Along the lines of research and education, a report we recently released for Efficiency Vermont, a very progressive group in the state of Vermont helping to advance building systems, and Vermont is doing that as rapid of a rate as any state in the country. This report is a very comprehensive report studying 13 essentially identical factory-built homes, manufactured homes in the state of Vermont, and studying them from the standpoints of air quality, comfort, and then energy on a very fine-grained basis. So you can grab that report from our website, and we hope that supplies you with a lot of information on how to build a very energy-efficient home. And for sure, if you can build at that level in the harsh climate of Vermont, that doing that elsewhere in the country is doable. And then our main activity, our main focus at Build Equinox is something we call a CERV, a smart ventilator, whose goal in life is to keep the indoor environment at a high quality for our health, for our productivity, and so you can find more information on our website about that. So new metrics for air quality, metrics that, to our way of thinking, help us understand what air quality means in terms of our health, our brain health or cognition, our quality of sleep, and overall our productivity. We feel this is a time when, because of sensors that are now available, sensors that you can buy online from Amazon, just little tabletop sensors that tell you something about air quality, to something like our smart ventilation system that lets you actively manage your air quality, that we now have the capability to see what's going on in the air around us and then to understand its impact on us. So I want to talk a little about why we feel these metrics are needed and the metrics we've defined. A bit about smart ventilation, although that's a whole topic in itself, and what the energy impact is when we manage our air so that it's at a much higher level of air quality than we typically see in our buildings. How does that value of our health and our cognition and productivity balance versus the cost of energy? Something that oftentimes has been maybe too much of a focus and at the expense of our health and productivity. And then we'll talk about these new metrics that we've developed. Over the years, as we worked in this field, as we talk about things like parts per million of CO2 and parts per billion of a particular volatile organic compound, people's eyes start to glaze over, and with good reason, that, you know, unless you're somebody involved in the field, that it's hard to have an understanding of what these mean in terms of our own personal lives. And so these metrics are meant to try to make these things a bit more understandable. And then looking at some field data. It's great to talk about things in theory, but what does that actually mean when we look at real homes? And we've been monitoring homes, myself personally, for over 40 40 years from my graduate studies at the University of Utah, where those were back in the days of chart recorders and audio cassette recorders collecting data, to today's technology where things like our smart ventilation system, CERV, that we actively have online data coming in from homes around the country. So how does field data, what does field data look like? And then finally, how about some real energy data to just see, can a home have excellent air quality coupled with being a top energy performer? ASHRAE, a society that we're active members of and participate in, but ASHRAE used to mean the American Society for Heating, Refrigeration, Air Conditioning, Engineering, but they switched from that because it's a global entity. ASHRAE is now just ASHRAE. And a couple of years ago, we had the privilege of hosting Bill Bonfleth, the president of ASHRAE at that time, when he visited Equinox House, our project house, and then my house. And as Brett mentioned, this house is a Zero Plus house. It was built in 2010. It's never had a detriment in energy from the get-go. So at this point, over 6 years, we've put over 10,000 kilowatt hours into the grid above what we need for our house and 2 electric cars. And so when Bill visited and then gave a seminar at the University of Illinois, I really enjoyed his emphasis for his term, which was how to look at a building environment and to take the emphasis off of designing a building to save energy, but instead how to design a building to keep occupants truly healthy and productive, not just a satisfactory atmosphere. This picture I took, this was in a library, actually in public library near Dublin, Ireland. And I just happened to look down as I was sitting on a bench. My wife is a librarian, and so anytime we're traveling, we visit libraries and we visit microbreweries. And so every time I want to visit a microbrewery, that means we're probably going to visit a library too. As I look down, you can see my foot. There was a supply air event, but it really doesn't matter if it's a supply air or a return air event. Vents just should not be in the floors. And you know, we're just hurting ourselves with some simple design things that we could easily avoid. And you can see if there's some critter down there having a little snack on top of the heating coils. And of course, I don't want to smell the bottom of my shoe, and I'm sure most people don't want to smell what's on the bottom of my shoe either. And Florence Nightingale, way back in the 1800s, had it exactly right. If you don't have good air in a house, you're going to get sick from any variety of things. It's common sense, and we need to put common sense in at the beginning of design. This next slide, again, a little quote from Florence Nightingale, and if you haven't read her notes on nursing, she was just genius. She was a statistician. She developed a number of metrics that statisticians use today, but she understood that you've got to have fresh air, and not air that's coming through a confused set of ductwork, air that's fresh and purging through whatever type of building you're in. And that if our architects and building designers, if they were also responsible for the cost of the sickness and the health of the occupants of that building, that we would have a much different building today. The lumber liquidators got to see this firsthand, how it affected their stock price, as they simply took somebody's word that the materials they were buying were low VOC, low no formaldehyde formulations, and it turned out they weren't. And the CDC estimates that cancer in homes with these will increase significantly. And we're just immersing ourselves in chemicals we've never been immersed in before. We're seeing changes to our health at a rate that's much faster than how genetics change our health. And with today's technology, with smart ventilation technology, we can see when things like this go into our homes, and we can hopefully counteract it with more fresh air, but also hopefully hold people accountable when they have said that a material is going to be this, and it turns out to be that. Just one example, this Vermont report that I mentioned on these 13 homes in Vermont, when the first few of those homes, the first 4 of those homes came off the assembly line, they were built with a countertop material, a Formica countertop material laminated on a particle board. And the Vermont folks who built these homes had ordered no VOC, no formaldehyde countertop material. And 3 of the homes, when the CERV was kicked on and ventilating, looked great. They showed that there were good low, no VOC materials in the home, but the 4th home, the VOCs were much different, much higher than in the other 3. We were finally able to track it down and found that the countertops in the kitchen, those had been damaged, the original one, and so a replacement was sent. And instead of sending a no formaldehyde countertop particle board, they had sent a regular one. Well, how would you know that without a sensor that could help tell that? They pulled out that countertop, got a no VOC certified one from their supplier, and the VOCs went down. And so this stuff is real as as we look at our building materials to make sure that they truly are what they're stated to be. Now, as far as ash rate, for residential ventilation, 62.2 is the committee that's defining ventilation standards. But what is very important to recognize is that it is a minimum ventilation standard, and it is not an air quality standard. They simply state that there is a necessity to have at least some minimum level of ventilation, and that roughly scales with the size of the house and the occupancy of the house. And the basis for this is decades old. It comes from the early part of the 20th century. Back in 1900, we used to have a ventilation standard that was around 35 cubic feet per minute per person. And that was based on things like tuberculosis and diseases that were running rampant and not having vaccines and other methods for dealing with it, better sanitation. And so they saw that, as did Florence Nightingale, that a high level of fresh air would help counteract the spread of disease. Around the 1930s, research at Harvard determined that we could lower that ventilation to about 20 cubic feet per person. And the motivation for that level was based on smell, on odor generated by the occupants. And basically, they put people in a small room. They would blow air through the room at 5 CFM, 10 CFM, 20, 30, 40, and they would have people smell the outgoing air from the room. And when 20% of the people were dissatisfied, that's what they considered to be an acceptable level of ventilation. Now, the person in the room, it's quite interesting as you read these studies. The person generating that pollution is a person of average size, about 1.2 square meters of body surface area. They're recently showered. They're wearing clean clothes and clean underwear. They're not smokers. And there's other qualifications so that it's a smell put off by a reasonably clean, and then a person who is not very active under what are called sedentary conditions, but basically office work or sitting in a chair type activity level. And of course, these conditions change as somebody's sleeping. It's maybe about half that level of pollutant output. When somebody is active, it's as much as 5 times greater in pollutant output. And so the person, their activity, how well washed they are, all of these things factor into how the odor may vary. Now, new studies since the 1930s, these studies are just coming in within the last 2 to 3 years, and we'll talk a little bit about those. But they're showing that odor is absolutely not a good way to define ventilation level. While people may be minimally dissatisfied with the smell, 20% dissatisfaction with the smell is not good, especially these days of Six Sigma manufacturing, where typically we're not happy if defects or things that don't work right are less than 0.00 something %. And so to think of a system in which you allow 20% to not be satisfied and the other 80% are not satisfied, they're simply not dissatisfied. This is just not, to me, something that seems acceptable. We can do better than that. So in smart ventilation, just briefly to summarize that, this just simply means that we've got sensors which are available today and at economical levels that we might afford for our homes that can measure pollutants of interest. In our case, carbon dioxide and then volatile organic compounds, but other things such as particulates. There's sensors available for describing and determining when particulates are above a range that that are reasonable for our health. A smart ventilation system can determine when it's nicer outside than inside, which for much of North America happens quite a bit of the year, as much as 6 months, maybe 10 months. And if you're fortunate enough to be in California or Colorado, you might find 10 months or more where outside at least part of the day is nicer than inside. And with smart ventilation, it sees that, and it knows that this is a time when you just want to maximize bringing in the outside air. You don't want any energy exchange. You don't want to go through any type of energy recovery, heat recovery ventilator. Just bring that air in, just like opening up a window and recharging your home with fresh air, and then turning it off when it's not so nice outside. With smart ventilation system, it's looking throughout your house. It's looking at the bulk air quality level, not in a specific room, but it's able to circulate and make every room, from a bathroom to a kitchen to every other room in your house, as fresh can be inside. And then with proper algorithms and intelligence built into the system, that it can also increase the energy efficiency above levels that you might get with conventional ventilation system, while also giving you better air quality than you would typically have. And then to add to everything else with a smart ventilation system, just like with a Fitbit or activity tracker, that it's able to monitor and archive your indoor air quality. And hopefully this gives us some ideas so we can see how to continue to improve the quality of the air in our indoor environment, as well as to see over time how accumulated effects may be impacting us. Just a couple of quick slides of trends. This top plot shows carbon dioxide and volatile organic compounds, total VOC sensor. This is a very high quality home. It actually is a certified passive house. And it has a constant ventilation system in it, the kind that's typical in many high performance homes, well-sealed homes these days. And without smart ventilation, without smart sensors operating a ventilation system, this is roughly a 2-week period, and you can see for about the first 5 or 6 days when people are there that it's exceeding 900 ppm of CO2 for almost all the time that people were home. And VOCs regularly also exceeded that level. And then these folks went away for about a week of travel. And the ventilation system, of course, then kept the house very good air quality, but it was too much ventilation at that time. And then when they returned, you can see the last 2 days, the pollutants build up in the home. The plot below shows about a 3-4 day period. And again, VOC and CO2 sensor in a home where the set point for a smart ventilator was set at about 1,000 ppm. And you can see that CO2 then triggered the ventilation to come on and not allow it to skyrocket to much higher levels. The spikes that you see during those times, typically on VOCs, these spikes are cooking spikes, and you can see that those were dissipated after those events quite rapidly. And then as you see the green stripes, these are, again, fresh air ventilation periods. You can see that as the house bounced along that threshold, that it was brought down and the air quality maintained throughout that time period. So this is the difference between having sensors that can monitor the air quality and then bring in air as you would need it. And then when fresh air isn't needed, you're saving significant amount of energy by not having the energy impact of ventilation. Just some sampling of homes that with smart ventilation that are exceptional in terms of their energy efficiency. When you combine the highest energy efficiency standards such as Passive House and FIAS type standards with smart ventilation, you get the best of both worlds. And these Vermont homes, you can see one in the bottom corner there. It's about a 1,000 to 1,200 square foot manufactured home, super insulated, super sealed, heat pump water heater, high performance, cold temperature, mini split heat pump, coupled with a smart ventilator. You end up with a home in a harsh environment that exceeds both Passive House as well as FIAS standards. The new FIAS standard dropping down to about 4,200 kilowatt hours per occupant in the near future. These Vermont homes spread over these 13 homes average 3,650 kilowatt hours per occupant. And the Passive House standard of in English units about 11 kilowatt hours per square foot per year, that these homes in a harsh climate and in a small home, which is even more difficult to manage, average 9 kilowatt hours, a 20% reduction over Passive House requirements. Looking at a history of house energy, where we have been and where we are today. Going back to the 1920s, and our university, University of Illinois, historically has been very active at that time, determining the R value of different insulations, what type of ventilation ducts, what type of central heating and cooling systems. The very first air-conditioned research house in the U.S. is on our campus, and it is still there to today. It was a house that back in the 1920s and 30s, they would load 200-pound blocks of ice into the coal chute and blow air over it to see how much cooling would be required in order to keep a house comfortable. This house in the 1920s typically didn't have insulation. It had single pane windows. It had infiltration levels, blower door infiltration levels of 30 ACH, air changes per hour, at 50 pascals. This house you didn't keep comfortable. You'd keep the parlor comfortable. If you had kept the whole house comfortable, you would be using about 150 to 160,000 kilowatt hours per year in our climate. The people energy load was tiny. There weren't as many things as we have today to power, but really the energy requirements for keeping the house comfortable were the climatic ones. As we moved to the 1950s, when we started insulating and putting up storm windows and reducing infiltration, getting to a level of maybe 10 air changes per hour, we got down to a level where now we could keep the house reasonably comfortable and maybe using about 30,000 kilowatt hours per year, or a cost of maybe $3,000, $4,000, $5,000 in energy per year. Moving on to 2010, and C stands for conventional construction, well-made, good conventional construction versus super performing, super sealed, super insulated, but economically designed type residences. We see that there's not such a big energy difference between the two, at least in perspective to where we've been. For sure, relative to conventional construction, that today's high-performance homes will drop us maybe to about 50% of that energy level. And I use 2010 as this metric because that's where I started seeing at conferences where prior to 2010, builders and building designers are scratching their heads on how to seal, how to insulate, how to avoid thermal bridges, how to get to a good level of energy performance. And as of 2010, I don't see that as a constraint. I don't see people banging their heads against the wall wondering how to build an energy efficient home. And now, as of the past 2 years, I'm seeing this wave of interest. Now, how do we design a healthy, comfortable home? And that's where I think your interest is now as well. I just see a question popped up on how leaky or airtight the building or houses are on slide 22. Hopefully that shows up that going from 30 ACH to 10 to, for the conventional home, that would be about 6 ACH. And then to something that meets Passive House and FIA standards, something that's 0.6 air changes per hour or less. And something to note on that is that even when a house is at 0.6 ACH, the infiltration in that house varies a lot with weather. When you're under fairly calm conditions, say a wind of 5 miles per hour or less, you might have about 5 to 10 cubic feet per minute of infiltration moving through that home. When you have a wind speed of about 20 miles per hour, that 4 times factor in wind speed turns into a nearly 8 times factor in infiltration. So now you have about 60 to 80 CFM of airflow infiltrating through your house. And this may actually be enough to manage the fresh air needs in the home. And with smart ventilation, that it will detect that the air quality is fine and not continue to run the ventilation at a higher level. Similar to if you have kids that are opening and closing the door, or you have pets and you're regularly lighting them in and out of the house, that these also are putting fresh air into your home that may not need to have so much additional ventilated air brought in. To also put things in perspective, let's think about the health costs. And for those of us who dream of getting the United States and the rest of the world to having all high-performance residences, when we reach this standard, and it is an economical standard, when you put economics in properly into the design, you'll find that your monthly bills for your mortgage and your energy will be less than a conventional house with higher energy bills relative to the house construction. But when you take this standard and you assume throughout the country that we can reasonably hit 4,000 kilowatt hours per person, and we have roughly 300 some million people in the country, and energy, solar generated energy, let's say 12 cents a kilowatt hour, but the reality, as I mentioned, is really now about 8 cents a kilowatt hour without any tax credits. This tells us that our residential energy costs will be about $160 billion per year. And if you read our Vermont study, you'll see that about 80 billion of that will be for people and their activities, their hot water, their computers, their televisions, their fish tanks, and cooking. And about $80 billion will be for climate. Now let's look at that 160 billion. So, and look at the cost of getting sick. Seasonal influenza costs us $80 to $90 billion per year. And there are studies that show better fresh air, better comfort condition control, that we could cut that in half. And it makes sense. If we have proper ventilation that decreases or dilutes the concentration of contagions, in addition to carbon dioxide and volatile organic compounds, that we're not going to get sick as often. Asthma now affects nearly 10% of the population. Northern latitudes are affected more significantly than southern. Northern latitudes, we shut ourselves in our homes more than we do in southern. We keep our houses closed up more than we do in southern. And this basically means that about 25 to 30% of our households, and most likely some of you, whether yourselves or people in your family or your friends, know somebody with asthma, and this is about a $50–60 billion per year cost. And it's something that's doubled over the last 3 decades as we've made our homes better sealed, better insulated, and then in this modern world of chemicals that we make things out of that we have not immersed ourselves in before. I feel with better ventilation, with smart ventilation, we're going to be able to return back to at least 5% and hopefully even more. But just think of that cost savings between not getting the flu through a natural means of better ventilation and reducing asthma, again, through better ventilation. And just to make a related point, refrigerators used to be one of the dominant energy costs in our homes. And now, with good emphasis and economic optimization of refrigerator design, the energy costs of refrigerators in the US is about $5 billion per year. Now, there's people in government still banging on the appliance companies to get another 10% out of that. But let's put that in perspective with foodborne illness, about a $50 to $70 billion cost per year to our populace. And the value of the food that moves through our refrigerators, roughly about $2,000 per household occupant, that's about $600 billion per year. And we waste about 20 to 30% of that food in our refrigerator. It seems to me that the focus on a refrigerator should be its real purpose, how to keep food nutritious and healthy and to keep it from making us sick. And we need more emphasis on that and not make the emphasis on its energy. We're at a reasonable level of energy now. Let's go to this bigger problem. And in our homes in a similar manner. We know how to build energy efficient, cost-effective homes. Now let's focus on our health and our comfort and productivity. Speaking of productivity.
Hey, Ty,
yep.
Could I, if you want to go back to that page real quick?
Yeah.
And I just want to make sure I catch this, and maybe everybody else might be looking too.
Yeah.
Those 2 middle bullet points. You know, let's say, let's just say you take the average family, right? And you consider the fact that seasonal influenza and asthma are primarily impacting people on, one side, the beginning of life or near the end of life, right? I mean, that's usually where those impacts really come in. It's not that people aren't impacted in the middle of their lives, but just considering that too, overall, what would be the number you would say, could, 50, 20, 30% could be reduced in having this smart ventilation on average?
Yeah, there's, like on asthma, it's a complex issue and a lot of discussion on where does that start from pregnancy through early life, and then what are the things that, set up that type of response within our systems, that we call asthma. On top of then avoiding asthma attacks. And you're definitely correct that, for example, in youth, there's a higher fraction, and I don't have that number off the top of my head, And you also find that in inner city environments that, again, where for various reasons people may not be getting outside to get sufficient fresh air, and they may be keeping themselves sealed up in their homes, that the incidence of asthma can be much greater. I have attended one presentation at the National Healthy Homes Conference in which somebody from Alaska, where they're seeing incidence as much as 30%. And there's also links to, in the populace they were studying, that there's a lot of indoor combustion of propane and not ventilated very well, and that this seems to have a link. So it's a complicated issue, and it has all of those variations, and so this is just kind of an average over that, and we need to look specifically at how to address that. But something has happened over the last 30 years within our environment at a time when smoking is at half of what it had been 30 years ago. Car exhaust is much, much cleaner than it was 30 years ago. And our factories and our power plants are much cleaner than they were. And I can supply some other references from these studies. Institutions such as Johns Hopkins is one of the leaders in this research. Seasonal influenza, there's some very interesting studies showing that humidity is a very important factor, and that too low of a humidity, something less than 30%, tends to make the influenza virus longer lived and maybe more airborne, as well as drier humidities drying out the mucal membranes in our nose and not catching as much virus, allowing us to inhale, again, various complications. And then going beyond 60% or so humidity, that, again, there's other things that seem to kick in and make that a less healthy environment, but that there's kind of this nice viral minimization window between around 30–40% and about 60% that seems to be a good range to try for. And then one of the papers I'll cite in a little bit here, where they've studied the impact of ventilation on sickness, that for sure there's a direct correlation on getting sick and the ventilation level in buildings and homes.
Great. Thanks, Ty. And I didn't want to
that's fine.
Too long. I actually had another question, and then I saw one came in that was pretty much in line with what I had.
Yeah, and I see a bunch of questions coming in, and hope that we'll get to those, and or that we can get answers out to you regarding these too.
I did want to bring up and just real briefly, this idea of cities, because we know in some degrees cities the air quality is getting worse outside.
Yes.
So when we're asking people to hide in their, we're saying indoor air quality is terrible. So let's say we do everything we need to do to improve that indoor air quality, tighten the house up, reduce the emissions, put in a smart ventilator. But then we're, presumably we're talking about ERVs, HRVs, drawing in air from outside.
Exactly.
What's being done to, what's being done to ensure that that bad air from outside coming in is being cleaned?
Yeah, you're exactly right that in some sense, you cannot have air in your home that's better than the reservoir of air surrounding your home. And so things like CO2 and VOCs outside without some type of other scrubbing device, which you should interpret scrubbing as meaning, like in the space station or a submarine, as requiring energy to create, say, a healthy atmosphere inside. What we can do with ventilation systems, though, is to get rid of the unhealthy particulates outside, and what that leaves us inside are mechanisms within a home that create particulates, such as cooking or dirt that's come in on our shoes and other dust, but having the ability to filter that air as it's moving through the house or exhausting it, and so, but you're exactly right that outdoor air needs to be cleaned up. To my way of thinking, we can't have electric vehicles fast enough, solar-powered electric vehicles, which are much more economical than gasoline-driven vehicles at today's prices, and that these are going to do remarkable things to our outdoor environment. And we need landscape architects and the importance of making the outside conducive to going outside from your home, just so you can get a lungful of fresh air and clear your head and not be adding pollutants to your own home. The more attractive and secure and safe we can make the outdoors for people, the better off we'll be. On our productivity, if you lose 2% of a workday, of an 8-hour workday, that's only 10 minutes. But if you're paid about $50,000 an hour, or $50,000 a year, $25 an hour, 2% productivity is $4 a day. As I mentioned, in these homes that we can aspire to, these economically high-performance homes, these cost, in solar energy terms, $1 per day to operate for all of your energy needs. So 10 minutes of a human's time is 4 times their daily cost of the energy per person. And we know that we lose productivity from these new studies, from CO2 at levels that we used to think were benign, from VOCs and how the soup of VOCs interact with things. And there's 4 papers on our website that you can find, and I won't go into their details, but you can download these, and these may, for sure they'll provide you some additional references. And I see there's some questions on studies for asthma. In our newsletter for Build Equinox, you'll see a review of a paper by the late Professor Ole Fenger from the Danish Technical Institute on what is air quality. And he has some very good reference links there for asthma and how that's tied into things like phthalate concentrations and other plasticizers and substances in our homes. But these are just the 4 papers that, just the headlines for you to see. Some papers that are more directly relevant to health, brain health, cognition, productivity, and sleep, which also impacts productivity. And this slide is from really what I think is a landmark paper by William Fisk at Lawrence Berkeley Lab, Professor Satish from SUNY, State University of New York Medical Campus, and their co-authors, and follow-up studies with Professor Satish and Professor Allen out of Harvard School of Public Health that have just added an exclamation point that carbon dioxide impacts us in several of 9 cognition-defined areas of activity at levels that we used to think carbon dioxide was essentially inert or benign. We used to think of carbon dioxide as a tracer gas, and it is not. If you're sealed in a mine, you're going to die from carbon dioxide poisoning before you die from lack of oxygen. It is a toxin, and it's something that impacts you in an imperceptible manner. You're not feeling drunk at these levels. You're not feeling like you're performing any worse, but you are. And these studies, based on a quantitative cognition performance tool, show that absolutely that as they repeat it with different people, as they repeat it on the same people in these blind studies, your ability to perform is impacted at very low levels of carbon dioxide, far away from those that kill you right off. And these same folks linked to these productivity and cognition studies, they've run these cognition studies. This is not an IQ test. This is using your thinking to get things accomplished, to do everyday tasks. And they've shown that this test that they've applied to thousands and thousands of people over a number of decades, that earnings correlate with cognition performance. And when they apply the cognition gains based on going from minimum ventilation standards, what are nominally about 20 cubic feet per person in a building, defined by ASHRAE, to 40 cubic feet per minute per person, that your earnings could increase by about $6,500 per person. Now, the reality of it, if somebody is annoyed by other things, or maybe they're playing video games instead of working, maybe they're getting a higher score on their video game rather than that showing up as real dollars to the company. But the dollar value is there. And this is just on a commercial basis, a study that we performed at a local business, that about a 25,000 square foot facility with a fair number of employees, 120 people, has an annual payroll of $6 million per year and a pretty healthy utility bill. It's a service center and also a data center, and about half of this energy cost is for running the computer center, and that's about $88,000 per year. But just look at how much you're paying for people in that versus how much for energy. And then from our study, this brown line shows our computer simulation results for this building, and the green line shows the actual. And this little inflection around lunchtime, we didn't account for, say, 20, 30, 40 people leaving during lunchtime and coming back in, but we can build that in easy enough. We just wanted to see that we were catching the dynamics of this building's air quality properly. And then when we applied an algorithm that put in a smart ventilation system, we found, first of all, that based on these cognition studies and the value of human productivity, that we could save this business about $750,000 per year. And if we were off by a factor of 10, just simply 1% improvement in productivity, that annual benefit is essentially equal to their utility cost. And the interesting thing in this case was that we found that we would actually improve their energy efficiency by a couple $1,000s per year, but we didn't impact it. And on a residential case, again from our simulation modeling, using smart ventilation, a home that would ventilate to 1,100 ppm of CO2 for its occupants, and this is a 2,000 square foot home located in Urbana, but similar results occur for most of the country. A fairly high performance home with well sealed and then heat pump water heating and comfort conditioning, that as we would improve the air quality, that the value based on the cognition performance, now do you gain $5,000 at home by having 700 ppm rather than 1,100? Well, you have to think about that. Is a child studying, doing better on tests? Is there $5,000 more value in that? Are you getting things accomplished at home that then aren't going to take up other time, so you have some time to relax or some leisure? Are you making better decisions? I feel that this at least gives us a scale, and so that as we see about improved air quality, and that's going to cost maybe about $50 more because of the higher ventilation rate, that it does have that value. So getting on to the metrics, and there's not a lot here as far as the metrics, and I hope you will check out our website because the metrics there are live metrics. They're taken from Equinox House, so you can see the raw data from Equinox House on temperatures, humidities, and CO2 and VOCs, and then you can see its history based on these metrics that we're introducing. And there's three areas as you would look at these metrics, what we call personal metrics. But for example, a high level of CO2, it impacts you now. It impacts you today. It's not next week. It's not 2 weeks from now. But you're going to have that impact now. And the same for VOCs. Based on these cognition studies, they put people in a room, and within a very brief time of that room being equilibrated at a certain level of VOC or CO2 level, that their productivity, their cognition performance drops. And then on pollutant exposure time, not just what's happening to you now, but integrated over time, just like kilowatt hours on your electric meter, something that we can add up and then see as we look back on, say, a particular health problem, or over a large part of the population as we accrue enough of this data to see how to improve our health overall as a populace. And then finally, just the basic IAQ data and statistics to help those who want to have a more basic understanding to have that data. Now, just blowing up the personal metrics, we put in VOCs, and we put that under health because these will impact your health. In cognition performance, we focus on the CO2 levels, and then sleep quality, our CO2 levels, but defined between sleeping hours to make sure that at night air quality is kept just as good as it is during the day. And what we mean by having this go from 0% to 100% is that at 0%, this means you're meeting the minimum ventilation standards of ASHRAE. And as you improve your air quality in terms of CO2 and equivalent VOCs towards 600 ppm, a level which currently seems from recent research, a level where you're minimally impacted by pollutant levels, that you're at 100% air quality level. And so whenever you're at 0, you're at minimum ASHRAE ventilation, nominally say 20 CFM per person. And when you're at 100%, you're finding that your air quality is being maintained at 600 ppm or less. And what we see on this graph are over the, say, past 4 weeks for this particular graph. And then these dashed lines are the CERV community or smart ventilation community that we're monitoring, what their average is. So you can see how you're doing relative to your smart ventilation neighbors scattered across the country. And on accumulated health impact, here it takes a little more analysis to do this, but we define 3 zones. This yellow zone is the ASHRAE zone from the 62.2 ventilation standards. And at the one end of the ventilation table, you would accrue about 72 pollutant hours per day. And these are combined volatile organic pollutant hours and CO2 pollutant hours. And when you're beyond the yellow, you're in a range that we define as poor air quality, but you're not even meeting the minimum of ASHRAE ventilation standards. And when you're in the green area, you're exceeding ASHRAE ventilation standards. And then this bar chart is showing you the same data over the past 4 weeks. What we use to define this pollutant exposure, we have a scale such that when you're less than 700, and I can see that when we're adjusting slides to fit the format here, this bar moved over. The vertical green line should be aligned with this, that when you're less than 700 parts per million, that you're not accumulating, say, pollutants that are significant. And when you're greater than 700, at 1,000 parts per million of CO2 or VOCs, we define that as an exposure unit. And so that if you're exposed for 1 hour at 1,000 ppm of CO2 or VOCs, you have 1 VOC or CO2 exposure hour of accumulated pollutant effect. And as we build up over a day, over years, these exposure hours can be added up. And so we can look back over a year and add those up just the same way the utility adds up your kilowatt hours or therms of gas usage. And then finally, the basic IAQ statistics, just so you can see what your parts per million of carbon dioxide and VOCs are, and then their relative level, which tells us a lot about what's going on inside of a house. Now, I do want to comment on the VOC. The sensor that we use is a total VOC sensor, and the way this sensor is calibrated by the sensor manufacturer is that they use 4 chemicals, things like acetone and terpenes, and in a ratio that mimic the main chemicals that our bodies, which are chemical reactors, emit. And when one person emitting CO2 at a level that results in a certain CO2 concentration within a room, when the sensor is calibrated to its total VOC level, equivalent to that CO2 level, they use the same scale. The reality is that the VOCs that are in this mix for the calibration are in the parts per billion range. But this helps us see so that when, relative to our respiration, when VOC levels on this scale are greater than CO2 levels, this is typically telling us that we have other sources of VOCs occurring. And when these VOC levels are less than the associated CO2 levels, this is a house in which, if it's an all-electric house, that humans are the main source of VOCs, our BO, the things we're wearing, things like that, our activity levels, our cooking, that these are the main sources of VOCs. Now, the reason why VOCs might come out less than 1, here you can see the ratio for the sample data is 1.2, but we see a number of homes in which it's 0.8, 0.9. And the reason why VOCs might be less than CO2 is that first, it's a clean home without a lot of off-gassing from furnishings, not a lot of cleansers or cosmetics or pesticides or herbicides or other chemicals maybe being released. And so that the main source of VOCs are the humans. And VOCs are reactive substances. They break down into water and carbon dioxide. They get absorbed into furnishing materials, possibly getting reabsorbed, possibly getting broken down. They're photochemically destroyed by sunlight. So there's a number of things that get rid of VOCs, or they recombine into other things, reducing their level. While CO2 must be removed through dilution without other chemical means of reducing it. Now, when you have combustion in your home, like natural gas, if you're not cooking something like Cajun or something very odorous, the CO2 is going to outweigh the VOC pollutants, the unburned hydrocarbons, and other associated pollutants from the combustion. But when you're cooking something that's quite odorous, the VOCs might take off and be in the lead. But typically, you're going to see a much, much elevated level of pollutants with indoor combustion.
Ty, can I, on that combustion piece real quick, do you see a difference if especially the water heater we see all the time isn't sealed to combustion?
Yes. Yeah, you know, it's kind of interesting that as we've gone to sealed combustion for like water heaters and then furnaces, we used to see, well, what we see in homes with older furnaces that have internal air for combustion, which means as they're sucking air into the furnace, that they're also sucking air into the house through windows and that throughout the house during the winter. And a house with an older furnace actually will have better air quality than a house with now the sealed combustion, just because that furnace sucking through 200 to 300 CFM of air through it. And in these same homes with older furnaces, we then find their air quality in the summer when they're in air conditioning mode and not sucking through the combustion air, that their air quality is worse in the summer than in the winter. But with sealed combustion, you should then have some type of ventilator in a home. And one of the myths that people propagate and people think are true, but it absolutely is a myth, is that a leaky home is not a home with good air quality. Where the leaks occur and where you live are two different things. And that takes us to this slide, in which we do a lot of indoor air quality assessment in homes around the country, and this is from a dozen or so homes over a 2-week period, but scattered throughout different times of the year. So just day 1 to about day 14 to 18. And on our pollutant hours per day, our metric that is integrating the amount of pollutant that you're exposed to throughout the day, you can see that many of these homes are regularly exceeding this 24 pollutant hours per day, which is what the ASHRAE standard would get you with nominally 1,000 ppm of CO2 or VOCs. So these are leaky homes. A good home in this mix is about an air change per hour of 6, and these homes typically are above that, say around 10 or so. And looking at a home with a smart ventilator that senses pollutants, now this data is taken from January 1st, and over the course of a month. And the reason January is selected for these homes, again scattered around the country, is that January is a cold time of year when people have sealed up their homes, and these homes tend to be high performance homes, so very little infiltration. You can absolutely see the difference that on a sealed, in a very well sealed, very well insulated home during the winter time when your home is closed up, that the air quality doesn't exceed this very often. And this is January 1st. Here's somebody partying away and maybe packed with people, lots of cooking, not enough fresh air in the world to keep that house at a good level. And then here's the following weekend. New Year's was on a weekend for this past year. Again, a time when some of these homes are loaded with people, and but still the air quality being maintained quite well when you can sense it and monitor it and measure it. And using our radiometric, and again, the conventional homes on that metric, and you see a bunch of them in this range, as well as a number of them exceeding that range. And then when we go to using smart ventilation combined with this metric, and this is for that January period, here's that home with a lot of partying. It was dominated by VOCs, so I'd say it's cooking, while the CO2 pollutant exposure hours per day are actually not so bad. But you can see that they're largely clustered in at this time period of the year. And then just to end on how the energy looks in these homes, here's a lot of data. This is data from our Vermont report. But these are the homes that average about less than 4,000 kilowatt hours per occupant. As a home overall, these homes are between 4,000 and 10,000 kilowatt hours. And here's Equinox House here, a 2,000 square foot home. Also, Illinois is a harsh climate. And then these are well-built modern homes, about 2,000 square foot homes. This just shows these are the type of homes that have poor air quality. They're pretty well built, pretty well insulated. They're going to have about a $2,400 to $3,600 a year utility bill, typical of conventional homes throughout much of the country. Not as low as it could be, but the air quality is not as good as it could be as well. So finally, sorry for going over here. I hope most of you have been able to stay along. That we're at a time where technology allows us to automatically ensure that our air quality is being maintained in an excellent manner. These new metrics, we hope, will give people now for themselves information that may be valuable for understanding why they're feeling better, why they're feeling worse. And as they're immersed in these pollutants and their exposure accumulates, that the archive data will be important for them personally, as well as for the general populace. I mean, this type of information can be valuable to medical and public health officials for understanding what levels are truly keeping us healthy, what levels should we shoot for. And that we can quantify this, we can also start seeing that these two neighboring homes supposedly built the same, this one's very polluted and this one's not. What happened? Did somebody substitute something in cheaper? Did somebody not properly construct it, leading to problems in air circulation and air quality throughout the home? And then finally, we're just at the beginning edge of this for the research that we need and the interaction between real data that we're now able to collect, coupled with the basic research going on at our great laboratories and institutions, that we're truly going to be able to help ourselves live in a healthier, more comfortable manner. on less energy in a solar-powered manner throughout our country and throughout the world. And thank you very much. I see there's a whole bunch of questions here, and for whatever time we have left, I'll try to answer as many of those. And so let me maybe start.
Hey, Ty.
Yeah,
I got you covered there.
Okay.
Why don't we just real quick? So it sounds like, Ty, we got a lot of questions here. And feel free, everybody, to drop some more questions in. Ty, can you all right with sticking around for a little while?
Yes, yeah, for sure. I'm fine on my side.
Perfect. Well, before we get to those questions, for those of you who do have to go, and for those of you listening online and on demand, just real quick, for those of you who want continuing ed, check your email, check your spam for your certificate survey. If you need GVCI, report it. If you need Passive House, here's the number right here. So make sure to screen capture that number right now as I'm talking, or write it down so you don't forget it. And for those of you watching on demand, go ahead and complete the 10-question quiz. So I'm not talking to any of you right now, just the on-demand folks who are watching in the future. Take the 10-question quiz, get a 70% passing rate or retake it, and you'll be able to pick up your CUs in that way. So yeah, I went through and I've been writing down all these questions and bundling a few of them together. So that way we've got it pretty organized here.
Great.
And one of the ones that came in, or two of them, fairly interesting, I guess, and just thinking of a smart ventilation system, you know, how do you operate those? And then the other question was, which I think was very interesting, is what are the ingredients? What are these things made out of? And I'm wondering if the speaker, or the question is coming to the question that I have. You know, I've heard some horror stories of ERVs and HRVs. I'm going to pick on them and not pick on any particular companies, but I've heard that they actually can put pollutants in the air because of plastics and all sorts of other nasty things in them. So maybe you could speak a little bit to what ingredients are in these types of smart systems to protect our health, and then how they're operated, you know, very briefly.
Yeah. And so on the smart ventilation, and maybe one of the main differentiating factors between it and, say, a standard once-through ventilation system, whether ERV or HRV, but that with ours, we run a higher level of airflow, nominally 150 to 200 CFM, and about 20% of the time for, say, a typically populated house with people polluting it in a typical manner, that we would have about 20% of the time where we're in fresh air mode, and the other, say, 80% of the time in recirculation mode. Now, recirculation mode is very important because this helps keep the bulk of the house at a uniform air quality, as well as for these homes, which we're seeing more and more of, that are using point source comfort conditioning, like mini splits, low temperature mini splits, that this helps move that bulk comfort conditioning around. When you think of, say, a single once-through ventilation system, what you find is that if everybody is gathered in one room, and let's say with these low-flow systems, you're running maybe 40 to 60 CFM, enough on average for maybe 2 to 3 people, that the unoccupied areas of the house, fresh air is being dumped in there. It's not doing anybody any good. It's moving to whatever bathroom or exhaust vent is closest, and it's expelled. While if you have, say, 60 CFM and about 8 different rooms you've distributed, you're distributing maybe about 8 CFM to the occupied room. That's not enough if 2, 3, 4, 5, 6 people are in that room. And so you find that this recirculation plus this higher airflow rate is what's needed in order to make sure where people are at the time they're there, that it's being kept at good air quality. Regarding the materials that different heat exchangers might be made from, I agree with that, that polymer heat exchangers and permeable, whether permeable, as in the case of an ERV, or impermeable like an HRV, but we need to look at those both for what they may be absorbing. Some of these materials are similar to the filter materials in cigarettes, and you know that the different substances, they do not just uniquely pass through only water. Other things are passed through as well, and we need to study that more closely. And that's all I'll say about that. So we can go on to some other questions. Brett?
Great. Yeah, the other question we have comes back to what we've been seeing, what I've definitely been seeing as I talk to more HVAC contractors, and that is, how does electronic filtering play into all of this, or not even electronic filtering, but is smart ventilation actually just diluting the pollutants, or is it actually, basically essentially destroying them? Looking at UV filter, looking at some of these new systems coming on the market that put particles in the air that apparently are supposed to clean the air and keep it clean, like 1 feet in front of your face. What are your thoughts on that?
Yeah, I'm a big believer in fresh air, and we've got to make sure our outdoor air is clean, and then that's the air that I want to breathe. There are other ionizers and other things that are remedying maybe a situation that hopefully fresh air could take care of by itself. And there are say different situations where maybe you do want, say, a combination of filtration and ultraviolet light. Bill Bonfleth, who I mentioned, who's a faculty member at Penn State, is very involved in research looking at optimizing between filtration, getting rid of particles, and ultraviolet for sanitizing air in a cost-effective manner. And so if you look up his name, you'll see some very interesting research on that. But I'm a big believer in fresh air. Just to give you an example, we were doing a remediation study for someone in a very expensive condo, downtown Chicago, beautiful view of Lake Michigan, beautiful view of downtown Chicago. And one of the occupants just developed this mold sensitivity that was just deadly. And as soon as she would approach their hallway, she could just start feeling her skin tingle, and they had poured their heart and soul into remodeling this and turned it into a gorgeous place. Outside of the window wall was, some of the best fresh air with Lake Michigan on the other side of it. And she could no longer live in this home. And as we went in and studied it, we found that there's a lot of air flowing through the house, but the problem was the ventilation air was coming from the utility chases, from the elevator shaft, from the internals of the building. And just as Florence Nightingale said, you want air from without, not from within. So we were able to specify a remediation in which we basically just sealed up the apartment so that all of these perforations to the inside infiltration leaks were taken care of. And then so that their ventilation system was also then modified to get it down to a reasonable amount of air being pulled through. And then we added just a simple, above the transom, above their balcony door, a simple ventilator fan that made sure it was positively ventilated with fresh air from the outside. And where we had not met this owner prior to the study because she could not get close to her home, after the study was finished and we went to have a follow-up visit and do some more measurements, she greeted us at the door, and she said she just couldn't believe how much of a difference it made. But I mean, I'm just a big believer in fresh air, and it does good things to us.
Great, thanks, Ty. Going to some of the comments you had made about, especially even unoccupied buildings that don't have these types of systems in them. The question is, in an occupied building without active ventilation, would pollutants build up, and which ones?
Yeah, so, and I saw one of the questions was regarding radon, so I'll include that as well. I mean, CO2, there will be, some level of infiltration, and we do infiltration modeling and research looking at how it builds up. And so based on the number of people, and without natural gas combustion or gas combustion, propane or natural gas, CO2 will primarily be from humans in that room. Now, plants are great. There's a lot more studies to be done with vegetation in homes. In our house, we've got several dozen plants, but just because we love plants, but there's something about plants that while they reduce CO2, they don't do it at a level that they get you back to fresh air level. But they do take care of VOCs, and the associated VOC buildup with humans is quite significant. When you start smelling your house, or often you get acclimatized to it, but when others come in and tell you your house stinks, that's telling you you've got less than 15 to 20 cubic feet per minute of infiltration moving through your house. When your house smells like what you cooked a couple days ago, 2 or 3 days ago, that's telling you you have insufficient ventilation, and it's also not healthy for you. And so CO2 and VOCs are definitely going to build up, but it's a combination of the rate at which you generate the pollutants relative to the infiltration. And I'll mention on radon, that will build up as well. And the reason we don't incorporate radon into our smart ventilation system, and most likely why others don't as well, is that radon is highly regulated. About 25 states have their own regulation standards, and about 25 states are not regulating it. And so the variation of the regulations just make it difficult then to incorporate sensors. For example, a radon sensor, as I recall, has to be recalibrated like every 6 months. Well, if you think of putting some kind of appliance-like device or ventilator in your house, now you've got to have somebody come in and do a certification on that every 6 months. And it's a fairly expensive sensor as well. It just makes it difficult. Now, the good news, though, is that when you build a properly sealed house and you do the right things on the foundation and you seal up any cracks and any sump pits or other things in the house, your radon entering your house should be kept low, and the ventilation required to keep you healthy will also be a ventilation that will keep radon low. But at the same time, you do want to watch radon in those areas, such as where we live, that are quite sensitive to that.
Yeah, that's very interesting, and I'm glad you brought that up. I was going to ask that question because we typically sometimes recommend people put in those passive systems and then just activate them later if radon becomes a problem. But it's like, how would you ever know radon became a problem unless you took an initiative? So it seems like there might be some work to do in the future. Or basically what we just recommend is no matter what zone you're in, you should always just put in an active system no matter what, because we've even seen homes in the zone 1, I think it's the least issue zone, have massive radon spikes in them. So
yeah, it's very spotty, and it's also seasonally dependent. When the ground is saturated with water, underneath your house may be the more porous pathway for radon to escape, and when the ground is dry, you may not see as much. When the ground is frozen, different things will impact whether it decides your house is a good pathway for it to move through or not.
Yeah. You got some time for some more questions here?
Yes.
Okay, great. I mean, just talking about levels, great, perfect timing besides radon. What is it that smart sensor systems use to gauge where a safe level of VOCs might be?
Yeah, so on VOCs, and there's good VOCs and bad VOCs, and it's extremely complex. But so what's a good VOC? Well, if I'm sick and chicken noodle soup smells pretty good. And I start feeling better as I start, and maybe it's just psychological, but I think maybe, those nice home cooking odors make you feel good. And if you feel good, that's what we want. But at the same time, you don't want what may be good VOCs to get infused in your house and that your house starts taking on those odors, even though it may not have a detrimental health effect. And so we find that, at least with the total VOC sensor that we're using, that whether good smells or bad smells, or things that are detectable or not detectable, that we want to keep those at a reasonable level. And so the level that scales with CO2, that we feel that those should be kept below, say, 900 parts per million on our VOC scale with our smart ventilator, the same as where we typically recommend that CO2 levels are kept. But now, VOCs are also odd in that, what you can smell and what hurts you are two different things. You're not going to smell benzene at a level that is carcinogenic and bad for you. But interestingly enough, the level at which you smell petroleum distillates, like varnishing wood and things like that the terpenes and things that are emitted from that, typically your sense of smell is at a much more sensitive level than the level at which you're going to have a health impact. So there's some things in which your olfactory or your sense of smell can detect at levels before something becomes harmful, and then other things that you'll never detect. And this is the nice thing with having a sensor that can really just kind of look at this soup of things. Now, to add additional complications, if you take two pollutants, ozone and then limonene, and there's studies by the Danish Technical University has led on these, Bjarne Olesen and colleagues have been a leading institution, and you'll find some references from them on this. But you take limonene, which is like in citrus cleaner, smells nice, and have that at a concentration level that's, say, below levels considered to have an impact on health, and ozone at a level that is also not considered to have a detrimental impact on health. And you mix those together, and the limonene and the ozone react, and they turn into waxy particles that are in this 2.5 micron range that are inhalable and that are a bad pollutant. And now as you think of the hundreds and hundreds of different chemicals at various concentrations banging together and mixing in different ways that can impact us, it's an intractable problem. But the overall message, I think, is that we need to just keep the air fresh, and our metrics hopefully are a good first stab at what will be good levels to keep us healthy. But as we accrue data and archive data over time, and as more research provides us more definitive information about the things we're immersed in relative to what are okay levels and what are not, that we can adjust these standards as needed, and we can adjust the set points on a smart ventilator to handle that.
Great, thanks. And I guess the last question here in regards to Passive House, does the Passive House standard require these types of smart systems or IAQ metrics, and if not, do you see the program heading in that direction ever?
They don't require it, but we're in constant discussion with the FIAS folks, as well as folks active with Passive House Institute, and they see the value of it. It's a difficult thing to wrap their arms around, because as they look more specifically at certifying things, with a smart ventilator, it's not like, say, a single efficiency rating, and then you put that efficiency rating with a CERV rating, with a heat pump seasonal performance factor, and an R value for insulation and a window factor, and then you get a house that works well. A smart ventilator is changing throughout the day and throughout the year in what it's doing. The swing seasons, we're bringing in fresh air almost continuously, or cool evenings we're bringing in fresh air. And then during the hotter daytime, when the air is actually more polluted from our activities and dust and things like that, we're minimizing how much air might come in during the daytime. These are things that you just can't capture with the simulation models that are used for certification in order to capture how the efficiency of a smart ventilator makes up or how it gains ground on these other systems. A good report that you can download from Lawrence Berkeley Labs called "Homes Are Dumb Without Smart Ventilation." You can also access that through our website. This more directly gives you information about smart ventilators and just how they do gain in this energy efficiency, while also taking you to a new level of indoor air quality in your home.
Great, thanks, Ty. Well, that is all the time we have for questions. Thanks for sticking around. Thanks for everybody.
Yeah, thank you very much for hosting, Brett.
Yeah, well, and Ty, just tell us a little bit more if people want to contact you, if they want to learn more. Just tell us a little bit more about where they can do that.
Yeah, for sure. Go to our website, and you can contact me anytime at ty@buildequinox.com, and we're happy to answer any questions on this. And you'll find our newsletter online, which also has similar articles. For example, we've started a library of different types of chemicals and different types of materials that our CERV smart ventilation system can detect. And that's going to be an ever-growing list. But for sure, we'd love to hear from you and try to answer any questions that we can.
Very good. Thanks again to Ty Newell. Thanks to Build Equinox. My name is Brett Little, Executive Director at the Green Home Institute. Take care, everybody.
Bye-bye.